Welcome to the Women Only webinar series, the second of that kind on structural health monitoring for rehabilitation of structures in the era of digitalization. The first Women Only webinar was organized in the month of January. This is the second in that series, and we all welcome to this webinar. Coming to the webinar, which is structural health monitoring, there's an irony related to structural health monitoring. If you look into a small car, which is costing a couple of lakhs, is associated with lots of sensors to monitor it. But unfortunately, the building we stay in, the bridge we move on, the dam we construct, there are no equipment to monitor its health. It's very unfortunate. But now the scenario is changing, and we could see some of the strategic structures. To name a few, the Chennai Bridge, the Signature Bridge, they're all equipped with sophisticated structural health monitoring. The structural health monitoring for the developing countries is very essential because the infrastructure which we have built is now aging, and it is imperative to monitor the health of the structure. Structural health monitoring is nothing but the way we monitor our own health by visiting a doctor and doing some checkups where the doctor diagnoses by asking us to go through some of the tests and identify the problem. Similarly, the structural health monitoring is also done in the same fashion. First, there is a visual screening of the structure. Then, based on the visual screening, the strategic locations are being identified and tests are being conducted so as to see that exact problem related to the structure. Now, in the era of digitalization, the structural health monitoring, which consists of voluminous data, has now become easy for us. So the topic of the webinar is very apt in the today's scenario, in the era of digitalization. And I welcome Ms. Ritika, Ms. Sahana, who are the speakers of today's webinar, and Ms. Anamika Kadam, who would be moderating the webinar. So let me do my first duty by introducing the moderator to all the participants. Anamika Kadam has an experience of more than 25 years by actively involving in construction management of large-scale infrastructure projects, both nationally and internationally. She is well versed with all the standards related to Indian, British, ASTO, etc. She is currently serving as DGM in L&T in Phase 3A expansion project of Delhi International Airport. Being an active member of many professional organizations, she also authored a number of published articles related to construction industry over these years. She has an experience of working in overseas projects in countries like Abu Dhabi, UAE, Oman, etc., and closely working with international consultants like Aru, Hill International, Huawei, Larsen, among the others. So with this introduction, I'll hand over the platform to Ms. Anamika Kadam.
Yes, thank you, Vishalakshi ma'am. Let's welcome our young women engineers as speakers of today's session. Our first speaker today is Ms. Ritika Nanaya. She is a structural engineer currently working as assistant manager at Tata Consulting Engineers Limited, Bangalore. She holds a master degree in structural engineering and passionate about digital technologies. She started her career in oil and gas industry and then moved on to power, renewable and thermal sector at TCE, wherein she has been involved in several domestic and international power plants projects. She is currently focusing on structural design of the various facilities within the power plants. Considering the fast-paced nature of the industry, she firmly believes in the need to make best use of the latest developments and technologies in her field of work in order to deliver innovative designs with better quality. Before starting our session and inviting my first speaker today, let me tell you all that we would be taking up questions from audiences at the end of these presentations by our both speakers. Till then, please keep posting your questions in the chat box. Now, I will over to you, Ms. Ritika. Please start your session, please.
Thank you, Ms. Anamika, and thank you for the warm welcome. And I thank you, Indian Association of Structural Engineers for giving us this platform to present today. But Ms. Anamika, I would request you to kindly also introduce Sahana Gangal, because we'll be taking this presentation together, and
Sure.
She will initiate this presentation before me.
Sure.
Yeah, thank you so much.
Yeah, thank you, Ms. Ritika. Actually, we were thinking that her presentation will be next to you. Ms. Sahana B. Gangal is a structural engineer currently working as a senior engineer at Tata Consulting Engineers Limited, Bangalore. She holds a bachelor's degree in civil engineering. She started her career as an engineer trainee under the Young Engineer Development Program at TCE. She was involved in projects related to design and automation of structures by integrating the inputs from multiple disciplines and generating 3D models to optimize design effort. The work also involves generation of standard user interface forms using Excel VBA to reduce errors and to produce quality designs in less time. She is currently working in detailed engineering of international power plant projects. As a young engineer, she believes in continuous learning and application of new technologies in order to excel technically in the structural engineering domain. She perceives that application of digital technologies in structural engineering would be a necessity and priority in the near future. Yeah, you are right, Sahana. It will be a necessity, and this is actually the demand to sustain. Yeah,
Yes.
over to you, Ms. Ritika and Sahana.
Thank you, Vishalakshi ma'am. Thank you, Anamika ma'am. And I would like to thank Indian Association of Structural Engineers for this opportunity and platform where we could actually present our future vision or insights, what we hold in our areas, what we think is actually the future. I would like to share my presentation. Yeah. So is my presentation visible? I would like.
Yes,
Yes.
Sahana.
Yeah, sure. So let's start with Tata Consulting Engineers, where we believe engineering better tomorrow. TCS has, it was established in 1962 with 58 plus years of technical experience, and we have delivered around 10,000 plus projects globally for around 55 countries. We are widespread in different sectors. To name a few, it can be thermal, nuclear, renewable power sector, and the services offered are design and engineering, project management, digital advanced technologies, and project management. What I would like to say is now that the industry and market, everything is moving towards the advanced technology. This advent of advanced technologies taking over the industries. We always see that how we can optimize the process or solutions. So for this purpose, digital transformation is the need of an hour, and it's just not the need of an hour. I can surely say that that is the future of all the sectors or all the industries in future. And to highlight a few, even TC is moving towards this sector, and these are the digital point solutions currently offered in the power sector. I wouldn't really go deep into this. It was just for the purpose how even TC is actually looking forward to move in that area. So coming to the today's webinar is the topic, what we call it as structural health monitoring for the rehabilitation of structures in the era of digitalization. I would like to go forward and talk about the content. First, we'll start with the introduction of digitalization. What is digitalization? And then we'll talk about structural health monitoring. When then we'll see how digitalization can complement the structural health monitoring. And this is something which is of a future scope and the least explored area. I would like to suggest, and then we'll discuss about the process description, how the whole process is can be taken, and from here, my colleague will take over where she'll throw some light into the application to bridges and heritage structures. While we are just discussing on that process, we will also like to cite some real time use of this technology. And moving forward, yes, as I said, this is something which is still least explored. So there are a lot of challenges which have to be dealt and find solutions. So we'll talk about the challenges which we will be facing, and finally with the conclusion and what is the future scope. So let's talk about digitalization. What I told, digital transformation is what currently going on. In that, there can be digitization and digitalization. So what exactly is happening? Do you know that 94% of the data around the world is digital? So what exactly are this data? This data can be anything. It can be your images or any PDFs or any messages. Everything is converted to data. This is a huge amount of data. Okay, let's assume we have so much of data in hand, but what do we do with this data? Can we make some use of it? Can we can we actually do some research on this, or can we utilize it for our benefits? So that's where digitalization comes into point, where we can actually utilize this data, perform some analysis, a statistical model development, to bring out some insights, to where we can actually get the final decisions to improve all the improvise your business processes or business decisions or infrastructure operations, better infrastructure operation, cost optimization. There are, if I keep naming, I think there are multiple uses of this, and that list goes on and on. So how exactly is this digitalization taken part taking part in any of the process? First, as I said, what we do is the digitization, where the data collection happens from any analog to digital data, and this data has to be prepared. I will talk about more about this data preparing in the upcoming slides. And once this data is analyzed, we get certain decisions, we can make certain decisions based on the analysis we obtain. We can always see here there's a big data which is scattered with different colors or different, that says that this is a different type of data. Then we have to arrange it into a proper similar set of data, based on which we can make out the decisions. So to come now, I would like to say the what exactly we call it as a textbook definition, or a proper theoretical definition. Digitalization refers to enabling or improving process by leveraging digital technologies and digitalized data. So what is the purpose? As I told earlier, it can be automation, or it is increasing the data accuracy, or to we want some structural efficiency, or we have certain data we want to structure and collect it in a right way. So what will be the outcome of this digitalization? That is nothing but we want some optimized designs, higher process efficiency, and we cannot ignore cost always plays the prominent role in any of the businesses. So cost optimization can also be carried out, and also because of certain decisions, certain analysis, we can see that we can already foresee what is going to happen in the future. So we'll always have a better control on the business operations. So moving forward, I would like to introduce more about structural health monitoring. Vishalakshi ma'am gave us some insight about it. But like as she told, it's we are humans. When we are not feeling well, we go to doctors, and when we have an injury, we go to doctors. But what about the structures? Even structures have a definite life cycle. cycle. So beyond which, if we have to extend their life cycle, or in case of some irregularities and they occur some damages, or even they are injured, we have to make sure even that has to be taken care, or any precautions or any remedies has to be put in point, so that we have, for what the purpose the structure is at that point, it has to be it has to keep going till the defined cycle. So this process is nothing but the damage detection. Based on this damage detection, a strategy is made for the engineering structures. So it basically involves observations and analysis of system over time. It's When I say over time, it's not just for a week or a month, it's for over the years, where we can observe even the slight changes in any material or any geometric properties, based on which we can come to a conclusion. Okay, there are some abnormal observations which we can see. There might be a chances of some damage, or there might be some chances of failures. So SHM is a bigger process, which it's just not a one step process, I would like to say. It involves a lot of steps. First is operational evaluation, then moving to second one is data acquisition, normalization, and cleansing. After this is done, we go for feature extraction and data compression, and then we move forward for statistical model development. I would discuss in detail about these processes in the future further slides. uh, First, let's see how we discussed about digitalization, and we discussed about structural health monitoring. But how will actually digitalization complement structural health monitoring is the question. This is something, as I told, it's totally a new area, least explored area. I would surely agree with Vishalakshi ma'am, how she did say that before it was just visual inspection, and where we had to perform if we see something irregular in that part of the structure, we would then go for a non-destructive testing, that involves again a lot of um, uh, that's again vigorous process. But this can be labor intensive, and we are not sure that we are getting accurate results as well. And that was because until now there was limited exposure on this technology or data analytics, and manual assessment was, I would say, still manual assessment is still widely preferred. But I the good part is that sensor technology has paved its way to current what we call current generation or current industry, which is gaining, and which will be the future also as well. So what exactly happens in sensor technology is that we are using variety of sensors. To be specific about these sensors, these are very sensitive to any changes that is happening in the structure. So because of these sensitivity in these sensors, we can detect cracks or any abnormal level of stresses or temperatures, and we can know beforehand, okay, there are some irregularities or abnormal behavior. So how does this happen here? This is where digitalization comes into part. You gain the data, but can we actually analyze the data and bring out some meaningful insights? Can we predict that, okay, this is the actually sensitive parameter which we have to focus on, or this is a sensitive part of the structure which we have to focus on? So that's how predictions are made, or decision making is made, and or no further processes or any remedial measures for the optimization or strengthening of the structure can be carried out. There are variety of tools, but for as an application, it still has to be explored in the structural health monitoring. But good to know that now people are actually using sensor technology for data collection. So that's the first step towards the betterment of this process. Now I would like to move forward and discuss about the complete process of how the structural health monitoring can be carried out. Firstly, I would the first step is always operational evaluation. When we start a project, we should always discuss what is the scope of the project. If okay, we are doing something, what we have a building, what is this building for, what's its purpose? So even when we are deciding to set up a structural health monitoring system in any of the structure, we have to decide on what exactly we are performing the structure. Are we performing just to know about the operational or the environmental conditions, or we are actually assuming that there might be after a certain point there might we might experience a failure in this. This totally depends on the type of structure which is going to be monitored. And these are the few questions which operational evaluation focuses on answering. Firstly, safety is of major importance, and so that has to be seen, that installing these sensors, how what is the life safety of it. And also the cost, again, cost is always an important part, and is the economic justification. Initial cost of sensors can be high, but is it really justified? If is that cost justifiable for the over of years of performance, where at the end of the cycle can we actually improvise and extend the life cycle of this structure, is what this operational evaluation firstly tries to figure out. And how is the damage defined when we are actually investigating on the structure? So if we say for a bridge, we would say an irregular moments due to any vehicles or trucks, or dynamic loadings what we see. But in case of heritage structures, there will be certain, that's already a law, a very long period of it was built very a very long period back. So there will be already some problems in those structures. So we are going to monitor for more problems, because we have to preserve those heritage structures. So this scope also has to be defined in this structural health monitoring before we start with any other process. Then any structure has it's always subjected to, like, okay, not all structures are subject to operations, but yes, there will be certain operational scope of that structure, and as well as dependent on the location, environmental conditions also plays role. So we have to define that critical point where we are actually monitoring it. If we say, are we monitoring it for the operational time of the structure, operational time of the structure, or are we monitoring it for the environmental conditions, irregular environmental conditions, or are we doing it for the both? Under which system are we going to monitor is the third question, which has to be answered. And what are the limitations on acquiring data during in the operational environmental? If we have to talk about power plants or any other structures, obviously, like, we cannot yes, there are certain interval at which the data is collected, but at certain working conditions we really can't operate these sensors and gain the data on the right accuracy. So that limitations also has to be found out. So based on which all these questions, based on these questions, the complete scope of this structural health monitoring is first set up. So once this is done, what is the next process is we have to decide upon the type of sensors. Based on the scope, we will decide what type of sensors are we actually using, and the number of sensors and the location at which it is going to be placed. And how, once the sensor is placed, how do we take the data, what is the storage, or where are we going to store that data, and where is the transmittal hardware. And the most important point is the interval at which the data should be collected. Sometimes it can be for 15 minutes once, it can be 30 minutes when, sometimes it can be even every second the data has been collected. That totally depends on the scope of that particular project. And if so moving forward, like the sensors again are the main point in this structural health monitoring. They are you especially for SHM, there are particular type of sensor which are to facilitate this monitoring process, so that engineers can actually make decisions based on this data obtained. So when I say sensor for SHM, it's not just one sensor. It's a complete network of sensors, and that network can be in hundreds or thousands, not really in thousands, but 300s or 500s. So that depends on the type of structure, how big the structure is, and what has to be monitored, what are the critical conditions under which it is monitored. So I would like to also throw some light into the type of sensors which are widely used in SHM. First is the fiber optic sensors, where we use optical fibers either as a sensing element. They are very, very, very sensitive. This fiber optical sensor is a wired sensor, and it can be used to measure different parameters: strain, structural displacements, vibration, acceleration. So it can be used for majority of the purpose, I would like to say. And the next one is the accelerometer. We know that in cases of bridges and all, it is subjected to continuous dynamic loadings due to trucks or motion, like movements of buses or anything. So over a period of time, there are certain changes in this structural dynamic characteristics due to damage or any, any performance in that, any changes in that performance. So this accelerometer can be used to, determine this acceleration forces through single or multi-axis directions. The next one goes with linear variable differential transformer, where this is an electromechanical sensor, like if any difference in the loads or temperature variations, this detects it and finds the displacement, and this displacement can be measured from few mm's to few centimeters as well. The next one is the load cell. The load cell is basically any, it's again, like, load cell are, I would like to say, wherever you demand accuracy and precision, load cell is of prominent usage, because any little changes in forces, like, it can surely detect on the tension, compression, pressure, and torque part of that, this thing, where the whatever the measured is sent as an electrical output. So it is directly proportional to the force applied, so based on which we can make out, okay, there are some changes, or there are some, no, there are more loadings or than the whatever the initial calculated ones. Then we would, I think most of you would be familiar with strain gauge. It is used to measure strain due to any force or of an object or any movement. So these sensors are, widely used in both steel and RCC structures. Inclinometer is a slope indicator, where, a slight movement, subsurface movements, or any deformations are, recorded. So what is the major use of this inclinometer is, we can monitor settlement profiles in embankments or foundations or any other structure, where, this light moment which can actually cause huge failures, or, at least give us an indication, okay, this is not in a right way, this can have some problems. So that is a major application where we can use inclinometer. Temperature sensors, I would say, this is, I think, widely used everywhere, and it finds its major application during construction, where, curing temperature of the concrete has to be monitored while casting. So that's where this temperature sensors, and it basically works on a very simple principle: voltage is always directly proportional to the temperature raised. So based on this temperature variations, the voltage will indicate what is the temperature, or any uncertainties in the temperature. So that's how the application of temperatures and sensors are used widely in construction during the time of construction. So next, okay, now we are introduced to all the sensors, and we have so many data. When I say that the data is being collected for so many years, imagine the ample amount of data we have in hand, like billions, trillions of data we can have in hand, depending upon the cycle or the duration at which it is recorded. But what can be the abnormal variations is, sometimes due to operational or environmental conditions, there can be an abnormal data. So what do we do with the data? Let's say, if I have to give a very basic example, I have a number 1 2 3 4, and I have the fifth data, which is 100. And if I have to take a mean of that data, and adding all that, I would get something mean around 50. Is that the right mean? No. So obviously that abnormal data is something which has to be trimmed or removed. So this is nothing but data normalization, where we take the data and we see what exactly is, what is the normal data and what is abnormal data due to some triggered conditions which is not in our hand. So that process is nothing but data normalization, and data cleansing is nothing but to pass or reject this selected data from whatever this normalized data we are taking. The rejecting whatever the unrequired data and selecting only the required data is nothing but data cleansing. So once this is done, once we have a set of data that is normal, and that doesn't have any other variations or other abnormalities, now what do we do? So can now we have to be able to distinguish between this undamaged and damaged data. We have a data, but can we say this is an undamaged data and this is a damaged data? So yes, that is nothing but feature extraction in the area of SHM. So this is where exactly we have to identify, okay, this is the data I need. On basis of this data, I'm going to see where, okay, this is not performing well, or this has some problem, or this I can anticipate in the future. So how do we do this feature extraction? So one is, first method is we compare it with the first hand observations. Let's say we have a structure, let's say we have a simple bridge, and we have the first data. When we install the sensors, everything is in line, everything is perfect. So at that time, whatever the data is there, and once after certain years, let's say after 10 years or 15 years, obviously the bridge is subjected to a lot of dynamic loadings. There can be a lot of changes, or there can be certain displacements which are beyond the required threshold. So that time, what we look, we can see certain differences in that graphs or data, which are showing abnormal values. So we are comparing with the first hand data to the current data, where if we see any abnormalities, then we can say, okay, there might be some problem in this area, okay, there might be some problem at this point. Next method, I would say, is to, already you have a set of data which is already flawed. You're introducing that flawed data, where you're actually comparing that flawed data with the current data. So if the flawed data is actually matching with the current data, that means there is a flaw that exists. Or you induce all the, this flawed can be anything, that can be damages due to wind, earthquake, or continuous continuously subjecting the structure to dynamic loads. So this type of flawed engineering systems are introduced, where this data and that data are matched. And if there are slight, okay, there is a match in that, then we say, okay, there is some abnormalities that is happening. Since we have already removed this environmental and operational conditions, what we have is a normal data. So what can be anything else? We can clearly identify, okay, this is a damaged data, and this damaged data, both the damaged data are matching. Then we can say, okay, there is some flaw. So these are the two methods which we use in feature extraction. Moving forward is the data condensation. This is a continuous process. Again, I say, even after normalization, there is again a huge set of data. But it no I think it's more important, how, as I told, how are we going to utilize this data? Are we going to leave the data just right there? Are we going to just leave that data to that structure? Can we use it in the future? So if we are using it in the future, how can we save this? So there are data reduction, size reduction techniques. But again, when we compress an image, the quality of the image reduces. So this data condensation is the point where we are actually compressing the data, but we are making sure to retain that feature sensitivity. Whatever we have detected has to be retained, and which can be, even in the future, if we are using, that can be actually visible, so that we can actually bring out some or let's say we are using it for the feature extraction, the second methodology for some other structure, then we have to make sure that that sensitivity is actually retained. But this is again a very challenging task, and it has to be explored, and this process has to be developed more and more in a better way, or optimized way, I would like to say. And next is the statistical model development. This is where the digitalization is the major part. What we call nowadays is all this data science, machine learning, everything comes into point. And this is the least explored area in structural health monitoring or structural engineering also, I would like to say. But no, undoubtedly I can say this is gonna be the future. Without any other deviation, this will be the future, and this is how every process is gonna be done. Statistical model development is it's concerned with implementation of all algorithms that operated on extracted features, whatever the features we are extracting, out of which we have to make a decision. As I told, we have a data, but can we make certain decisions out of it? Can we bring out certain patterns on which we can identify any irregularities? So that's where this process comes in. uh, so this can be done in different categories. I would say this one is supervised learning and one is unsupervised learning. So these are the machine learning techniques. Very basically, if I have to say, since this is very much like not explored in structural health monitoring, if I have to throw an insight of how this can be used, let's say we have an undamaged available data from undamaged structure and a damaged structure. So what happens in supervised learning, everything is already fed. Okay, if this is the variation, it means there is some problem. If this is the variation, that means it will collapse. Or if this is a variation, there are chances that this is giving an abnormal behavior. So it's basically like, let's say you have a teacher, you're in a school, you have a teacher who has already learned everything, she knows the knowledge, and you are a student who is learning from that. So when you are having a data of a damaged structure and undamaged structure, but if there are any abnormalities, it will say, okay, this is abnormal, based on which it is trying to categorize. So this can be done in class, two this is of two types. Algorithms can be of two types. One is classification groups, regression analysis. So classification groups, I think one of the thing in supervised learning is every data set is defined, already defined. You don't have to bring in new data, but here this already defined. Let's say you're not a microbiologist, you have a set of fish, and you have the set of fishes are of different colors. So you don't know which fish is which, but you can still classify it classifying it based on size, colors, or appearances. You can still classify it. So that is how this classification of group takes place. When you are getting certain set of data, we have huge set of sensors, like thermal, some sensors are using for temperature, some sensors are using for displacement. So how do we classify those? So that is done in classification groups. Now when we talk about regression analysis, regression analysis basically a comparison. So one simple example, if I have to talk, is linear regression analysis. If you have a y and if you have a x, let's say you have 6,000 square feet area, and you are saying that cost around 4,000, and you have one more 8,000 square feet area, and you have around let's say that cost around 8,000. Now if you get a value which is in between, then you get a that will actually correlate between that and give you the value. So this is nothing but regression analysis. So this can be, already a developed pattern is there between the data. So this methodology can be used only when you already have a damaged data, and you have a developed, definite set of pattern. Unless until then, it's not possible to use this supervised learning. The next one is the unsupervised learning. We cannot always say that we'll keep getting the same type of damages, or we'll keep facing the same problems. Problems or anything can be no, everything can be obtained like newly. So what do you do for the new or any anomaly detection? What are we doing? Then we use unsupervised learning. So in unsupervised learning, we are not giving any commands, or we are not feeding any data. Here what happens, the everything is new, and the structure, let's say I have three parameters, then the structure itself has this whatever the data is obtained, this algorithm itself has to establish the whatever the relationship between these data, and how will they vary. So this is completely any outlier data or any novelty detection. That's where this application comes into part. And yeah, these are the two main algorithms what I would like to talk. And this is again, I would clearly specify it is the least explored area in structural health monitoring. So moving forward from here, I would like to request Ritika to take over, as she will be discussing on the applications and the examples more on this part.
Thank you, Sahana. I'll just share my screen to just view the other part of the presentation. Just let me know once the screen is visible.
Yes, Ritika, I can see your screen.
Yeah. Thank you, Sahana, for taking us through what is structural health monitoring, and how digitalization can complement structural health monitoring. So, and also a brief insight into the process of structural health monitoring. So after seeing this and after having a brief idea on that, let's move on to the applications of structural health monitoring to bridges and heritage structures. So we know bridges are the most commonly used infrastructure components, And the bridges are always subject to a lot of overloading, high level of stresses, and material aging as well. So when we design a bridge, we always design it for a particular level of traffic and volume of traffic. And it may not almost be true that 30 years hence, the bridge is going to be subject to the same amount of traffic. I mean, obviously, we always have a factor in place to consider this, but the traffic level is always so dynamic that the level of loading that a bridge can also be subjected to is that dynamic. So every structure, when the structure is subjected to some loading, or when structure is subjected to some abnormal loading, it always exhibits some warning signs. So how beneficial would it be to us if we can identify these warning signs, and if we could, if the structure could tell us that there is some damage happening here, and if the relevant engineer can go and observe the structure at that point of time and prevent some damage or prevent catastrophic collapse happening. So that is the reason why we look into structural health monitoring system being installed onto bridges in particular, or any other structure for that matter. So like Sahana explained previously, we can see this is the basic methodology of an SHM system. So we will install some sensors on the structure, and the sensors are going to generate some data. You are going to acquire some data from the sensors, and this data has to be processed, and you will be performing some analysis on the data that you acquire. And this can be done using a lot of softwares, a lot of data analytics softwares. And this, whatever data you have acquired and analyzed, finally has to be effective in helping you to take a decision as to what kind of rehabilitation or what kind of remediation needs to be done for that particular structure. So this is the idea behind installing an SHM system on a bridge. So for any bridge monitoring system, these are the four main components. That is a system control unit, a sensor unit, a software, and a communication capability. So let us see what each of these units mean. A system control unit, it is the hardware of the bridge monitoring system. So you could say that if you're using wired sensors, all the sensors are going to be wired to this particular unit. And this particular unit can be used to turn on or turn off the sensors. It can be used to record. So once the data has been acquired from the sensors, it will be stored on this system control unit. So in short, we can say that the system control unit is like the heart of the bridge monitoring system, where all the operations take place. And the next unit is a sensor. So sensors, there is a broad categorization of this. 4 categories, we could say, for a bridge in particular. There are structural sensors, environmental, traffic flow, and maintenance. So we'll just see a list of few of the sensors that we use for bridge monitoring. There are many more, and these are just maybe the most commonly used type of sensors. So the accelerometer, it is used to measure the vibration. The bridges are always subjected to a huge amount of vibrations. So the accelerometers are used for that. Deflectometers, it is used to measure the transverse deflection of the bridge. Strain gauges, it is used to measure the strain at a particular point. And with that strain value, you can obtain the stresses that the bridges are being subjected to. Temperature sensors, load cells, LVDTs. Seismic sensors are used to measure the strong motion earthquakes. And tilt meter, you have a pier or a pylon or any vertical element which is subjected to some amount of tilt. These tilt meters can easily identify that tilt values. So those are few of the commonly used sensors. Now software. So once you have that huge amount of data, this data needs to be analyzed. Some analysis has to be carried out on them. And how do you do that? Using a software. So for each bridge, so depending on the size of the bridge, depending on the location of the bridge, you will set up a different type of bridge monitoring system. It need not be like every bridge will have the same kind of monitoring system. So for each kind of bridge, there is going to be a different type of monitoring system. And depending on the requirements of that particular structure, you may have to develop a software. Say you're installing some vibration sensors or accelerometers on the bridge, your software should be catered to that, so that your software will read that particular signal generated from the accelerometer and tell you that this particular bridge is subjected to vibration, and how your software can analyze the level of vibrations that the bridge is being subjected to. Nextly, the communication capability. So when you have this amount of data, you need not sit at the site where the bridge is constructed. You need not sit at the site and try to do all this analysis. Obviously, you can sit at a different location. You can be elsewhere and you can analyze all this data. So for that, we need a good internet connection. So trying to transfer the data to the host computer, which could be at another location, is also very important. So next, we'll move on to heritage structures. So heritage structures are also very important because we know these structures might have been constructed about 200, 300 odd years ago, and it becomes very important to preserve these structures. So the monitoring of heritage structures is also equally important. And there are some challenges that are associated with the monitoring of these heritage structures is because we do not have sufficient information on the material that has been used. Usually all the heritage structures are constructed using, stone masonry or bricks, which we do not know exactly what kind of material they have used and what are the design concepts. And we do not have the drawings that have been used to build these structures. And hence it is a challenging task for us to do the monitoring or to install the monitoring system on this. So yeah, like I said, the lack of technical details and the structural condition of these structures, because of the lack of details, it becomes a challenging task. So what we do is when the particular authorities feel that the bridge, say after 100 years, the heritage structure after 100 years, they observe some amount of damage or cracks or something in the heritage structure, that is when they feel, okay, we need to do some level of monitoring in order to preserve the structure, in order to improve its performance or to improve its lifetime. So that's when they go in and they try to, so this monitoring system could be a long-term one or a short-term one. You can install it for about 3-4 years, collect all the data you need, and then you can perform the required analysis and then use your, the engineering, you can apply your engineering and try to come out with a rehabilitation technique for that. Long term could be, say you have a structure which is extremely important in terms of the country's economic condition or anything like that. So that time you have more funds to install a long-term monitoring system. That time you can go in for a long-term monitoring system where you install the sensors right from its inception until the time when you feel like the structure needs some monitoring. So these are some of the commonly used sensors for a heritage structure, that is LVDT, strain gauges, temperature sensors, and tilt meters. So we have seen the application of the technology for bridges and heritage structures. Now we will see some real-time examples. So this is a case study of a bridge in China. It's called the Jiubao Bridge. It is a tide arch bridge, and it has been constructed in the year 2012. So from the picture, you can see this is an extremely long span bridge. The span of the bridge is approximately 1,855 meters. And you can see a layout of the sensors that have been installed. There are hundreds of sensors that have been installed on this bridge. And the parameters that need to be measured for this particular bridge are it's more in number. So based on the number of parameters and the number of locations that you need to monitor, you can come up with a plan as to how many sensors have to be installed. You can just get a brief idea on where all these sensors have been installed on this particular bridge. So these sensors, like I said, for this particular case of the bridge, it is installed on the bridge to obtain the wind speed, direction, the environmental temperature, humidity, and the beam deflections, bearing displacement, etc. So totally 11 parameters were to be monitored for this particular bridge. And in considering all the 11 parameters and the different locations of installation, a total of 333 sensors were installed on this particular bridge. So you have a smaller bridge, you have a bridge of shorter span, you may not have to install so many sensors. So this particular bridge, considering the span of the bridge and considering the different parameters that need to be analyzed, they had to go in for a total of 333 number of sensors. Moving on to damage identification. So this is the next step. This is the most important step. So this was in the structural health monitoring system was installed at the inception of the bridge, not at a later stage. So the basic, one of the most commonly used methods here was to compare the model for a damaged structure and the model for an undamaged structure. So we could compare the modal parameters. So modal parameters like our mode shapes, frequency, time period, etc., for any structure for that matter, are functions of the physical properties of the structure. So we know the moment for an undamaged structure, we model the mode shapes or we model the frequency. We know that how the mode shapes would be for an undamaged structure. So we can assume that in the first few years of the structure, it is an undamaged structure. So post, say, 15, 20 years, when we actually try to compare the compare the modal shapes or the modal parameters for a damaged structure, we can clearly identify, there is some difference in the parameters, and that's why there is some damage, anticipated damage in this particular element. So each sensor will generate so much data that you can generate, or you can develop all these parameters and using a suitable software in order to perform this comparison. So this is just an example. So this bridge was built in the year 2012. So as of now, we do not have any data as to whether they have found any damage for this particular bridge or such. But then initially they did some comparison as to whether the sensors were performing well and whether the data that the sensors were emitting were, we could correlate it to the actual scenario of the bridge. So if you can just see this graph, it is a graph of a deformation versus time. And so you just observe this. So this is a 1-day graph. So you can see the amount of data that the sensor has been generating every minute or every 5 minutes. The sensor is generating data, and you can see the extent of data that has been collected. And you can see that, say around between 500 to 800, around that time interval, there is a peak in this deformation value. So how did the relevant engineers try to attribute to what did they attribute this reason was they say, okay, considering 0 is at 12 o'clock, at 0 o'clock, they say that the deformation is maximum 800 minutes past 0. So that means at around of 2 o'clock in the afternoon, the traffic on the bridge is so high that it leads to deformation on that particular bridge. So that's how they were able to identify, and they were able to actually see whether the sensors were performing well. So this is a very basic, very easy graphical method of checking the sensors. So later then the sensors were obviously used to monitor monitor the overall performance of the bridge. So this is another heritage structure. So like you can see in the picture, this is this is a palace in Split, Croatia. So this heritage structure, it was constructed hundreds of years ago, and say about 15 years, in the last 15 years, the authorities felt that there was some monitoring needed, which is when they started observing some cracking in the arches and in the columns or the main elements. So that is when the authorities felt that there was some level of monitoring that needs to be done for this particular heritage structure, so as to preserve it and try to improve the overall performance of the structure. So what they did was they installed a health monitoring system on this palace, and they collected data using a total of 17 sensors, and the sampling interval was about 30 minutes. And the data collected was for strain measurements, for displacement, etc. So you can see in this picture that how the strain gauges were installed and the displacement sensors were installed. So even there are many challenges in heritage structures. So you can't really install the sensors so that it ruins the aesthetics of that particular structure. And there are many challenges like that. So finally, they installed the sensor for a period of about 3 years. And between January 2013 and March 2016 is when they performed the structural health monitoring system. And all the data that was collected during this these 3 years, was used to finally perform analysis using this software called the LabVIEW software. Using the software, they were able to perform the analysis and finally generate the required damage scenario. So in the case of a bridge, what I explained was that the monitoring system was installed at the inception of the bridge. But here in this case, we do not have. So, and when you say after 15 years for that particular bridge, you can obviously compare the data, how the structure behaved in the beginning and how the structure is behaving now. But in this case, you do not have any previous data to compare with. So the method that they adopted was they set certain thresholds, like based on their engineering experience, they were able to set certain thresholds like the strain should not exceed this value, or the displacement should not exceed this particular value. So this is all on a lot of, this can be decided based on a lot of engineering expertise, and you require engineers to be a part of this project. You require the sensor, the person who is installing the sensors to even tell you whether the installation of sensor at this location is feasible. So this requires a whole lot of study goes into this to finally decide on what are the suitable locations of these sensors. So finally, this was for this particular palace, what they did was they set certain thresholds. And when the software, when the strain measurement or the deflection measurement or the temperature for that matter was going beyond that particular threshold, the software used to raise an alarm. So that time they were able to tell that at this particular point, at this particular arch, there was some damage which was, not normal. So that was when they could go and actually visually identify and try to rehabilitate that particular element of the structure. So, the examples that we have seen till now is for a bridge in China and the palace in Croatia. So now let us see some examples in India as well. So in the last 2-3 years, India has also tried to take a step towards digitalization, towards structural health monitoring using this digital technology. So you can see these are just news articles that try to tell us where the sensor technology has been adopted in India. One is a bridge in Tamil Nadu, and the other is a bridge in Kolkata. So the particular case of a bridge in Tamil Nadu, so a total of 41 electronic devices were installed on this particular bridge. And so the installation, the sensor manufacturers were asked to install these at suitable locations in order to identify and measure certain vital parameters of that particular bridge in order to give us a complete picture of that how the bridge is going to. So this the system was not installed when the bridge was constructed. It was installed at a much later phase when they felt that they could go on for a structural health monitoring system. So this is the case of the bridge in Kolkata. So if you can see in the picture here, the bridge which was located in the same place earlier had collapsed, and the reason attributed to this collapse was lack of maintenance. So when this happened, in fact, this bridge collapsed in the year 2018, which is quite recent, and the new bridge was constructed in the year 2020. So when they constructed this bridge, they realized that a lack of maintenance was one of the major reasons for the collapse of that bridge. And how do you tackle that problem is to try to install a suitable SHM system. So they went in for this methodology, this digital technology, where they installed some wireless sensors on the bridge, and they were able to measure the bridge's integrity by using some indicators like strain sensors and vibration sensors, etc. So this was how, so you can see a total of 30 smart sensors were installed on this bridge. And this is how they went about trying to improve the performance of this particular bridge. So obviously, when we adopt any technology, there are some challenges that we face. So big data is one of the most, one of the biggest challenges we can say, because like we said, the sensors are emitting data in the form of, every 2 minutes, every 5 minutes, you have, depending on the time interval that we are going to set, but every other 30 minutes or 15 minutes, there is some data that is being emitted. And just imagine you're collecting this data for a period of 10 years, 15 years. So what do you do with so much of data? Like, how do you actually use this data to analyze? So that is one of the biggest challenges that people face. You need to actually identify this data and identify the useful data, which actually can help you in aiding your decision making. Relationship between the measured data and system parameters. Yeah. So when you have your measure, supposing you're measuring the deflection of a particular beam. So how do you correlate this deflection that you measure to the actual deflection that, so when we do our analytical calculations, when we measure the deflection of a beam, we always have different parameters like the cross section of the beam, and we have the the size, length of the beam, etc., coming into picture. But how do you correlate this data that the sensor has given to the actual scenario of that particular beam? So that is also a challenge in this case. Now, uncertainty in environmental and operational conditions. So when you're collecting this data, not all the data that you collect is useful data. There is some uncertainty due to your environmental conditions, due to operational conditions, which can lead to some erroneous data. So this erroneous data has to be finally eliminated. So like Sahana explained previously, there are different methods, data cleansing, data normalization, where you can actually try to remove all the data which you feel is not useful. And finally, you have a set of data with you, which you can tell the software, and which the software can tell you how the actual damage scenario is. Smaller insufficient samples for damage scenarios and unsupervised learning provides low level of damage assessment. So like she said, like Sahana explained, supervised and unsupervised learning. So for supervised learning, we always have a reference, like we compare it with an undamaged structure, or we have a threshold based on our experience. We have some threshold with which we are trying to compare the data that we have. So, but in unsupervised learning, what happens is we do not have any known value. We do not have any known data for us in order to compare the data that is being collected from these sensors. So that is also a challenge for us in this current scenario. So finally, we move on to the conclusions and future scope. So after seeing how this digital technology has complemented structural health monitoring, we can say that this technology has actually paved, digital technology has actually paved a new path of structural health monitoring methodology. So earlier, when we used to go to the site and do a visual inspection of a beam or a building for that matter, it used to be labor intensive, it used to take more time, it used to be expensive as well. So this is a new path, a new technology that has evolved in the past few years, and it is actually proven very fruitful. And efficient design of a sensor network for application and structural health monitoring is a major milestone for the robust and effective system. The critical step in the new SHM approaches is to build an information system. So again, we need to build an information system where we can, make good use of that data in order to fuel our decision-making capabilities. And finally, so any system that SHM system that you design, it's not very easy to define. So when you say for that case of that bridge in China, it was such a long span bridge that you had to sit and actually evaluate the locations where you feel that the strain is more or the deflection is more. So any SHM system that you design, you need to actually finally come out with a very detailed, very effective location of the sensor, the number of sensor, and the type of sensor that needs to be installed. So when all these three parameters club together and you come out with a very effective way of structural health monitoring, that is when we can say that system is actually effective and the system is successful. And finally, the structural health monitoring using digital technology has proved to be fruitful in many countries. So we have seen that obviously foreign countries are using this, though digitalization is always a new topic for us and not much has been done in this front. But now of late, foreign countries have adopted this and they have tried to put effort into this technology. But in India, in the past 2-3 years, India has also taken a step towards this direction. But I feel we can do much more in this, and all the latest developments in data analytics and the softwares that we can develop in order to analyze, in order to generate a lot of results from these sensors. I feel that we can, by doing this, we can gain some confidence on our structures, and we can also prove, we can help development of our infrastructure, and which can also be very beneficial for us. So this brings us to the end of today's session. Thank you so much. And we are actually open for questions now.
Thank you very much, Ritika and Ms. Sahana, for such a wonderful presentation.
Thank you.
It gives us so many insights of the structural health monitoring through digitalization. Now I will straightforward. We'll go to the question and answers. Yeah. So first question is, are there any infrared sensors to monitor the crack progression?
Yeah, there are actually infrared sensors that are used. For crack detection. So these sensors can actually tell you the location of these cracks and the extent to which the cracks have been progressing, because there is some change in the homogeneity of that. Say you're talking about the crack in concrete, there is some change in the homogeneity of concrete, and so these infrared sensors can actually detect that change and tell you that there is a crack here. And also, along with infrared sensors, we have these acoustic emission sensors also, which can tell you, the length of the crack also. So these are some sensors which we can use for crack detection.
Right, Ritika. Next is crack progression can also be detected through acoustic emission sensors?
Yeah. So that's what I said. I think infrared and acoustic emission sensors are two of the most commonly used sensors.
Yeah, you already answered.
Yeah, crack detection.
Right. How the damaged data can be restored as original data?
What we say is data condensation. When I did talk about it, there are again methodologies in which we can actually restore that data back to the normal form. That's why I told that area still needs a lot of research, where compressing that data, even making sure that the feature is actually evident even in the future. But there are methods. Similarly, when we are compressing it, there are again methods to even bring it back to the original form as well.
Yeah, right. Right, Ms. Sahana. Next question is, what's the difference between normal foil type strain gauge and vibrating wire type strain gauges?
But can you just repeat the question, please?
Yeah, sure. What's the difference between normal foil type strain gauge and vibrating wire type strain gauges?
Foil type strain gauges. Okay, I'm not very sure on this, but definitely we can get back to you on this. If you...
Right. How can one ensure the reliability of data given by NDT instruments?
That's I think that's what we told, that because NDT is not reliable, we are actually shifting towards this sensor technology and advanced analysis, which is the future. Again, there are a lot of, I do see there's one more question. How why is what are the disadvantages of NDT? If I have to talk, we always go with visual inspection, and NDT can always give us only the surface damage detections, and it's again a very long process because the surface cannot be taken on any painted surfaces, and all the cleaning and every starting when we are actually installing it, everything has to be clean and prepared. That takes a lot of time and cost.
Yeah, right, right. Next question is, how is calibration of NDT instruments is done?
So actually here we are talking about sensors. NDT instruments are a little, on a different topic. It does not, it helps in structural health monitoring, but NDT is what you use when there's a damage on the structure, and then you go to the site and you try to find out the extent of damage. So here we are talking about sensors which try to give us some data which will help us to identify the damage prior to it happens. So that's what. So NDT calibration is generally, not a part of sensor technology.
I think that
Right,
is also one of the disadvantages what we
Yeah.
have. If it is not calibrated at the right point or right way,
So
then we
that's why
always get
we.
unreliable data or the end
agreed, agreed. Yeah,
measurement.
yeah. Is there any relation between non-destructive test and destructive test?
Yeah, so destructive. I mean, it's non-destructive techniques are very commonly. So we can say, like I said, it's a part of structural health monitoring. Destructive test is, see, like the name itself suggests, you want to find out how the strength of a concrete block. What you do, you break it. You apply some load, you break it, and you find the strength of that block. But non-destructive is, I think we have some tests like the rebound hammer and ultrasonic pulse velocity tests where we try to not destroy the structure. So we apply sort of waves from the exterior, and we try to find out, okay, there's some corrosion in the rebar inside, or something like that. So that is a non-destructive technique, like the name itself suggests.
Correct. How would you monitor the health of a structure subjected to cyclic loading and designed for a particular cycles of life, say 2 million cycles?
Okay, so cyclic loading, So cyclic, say, for example, we have a bridge. The bridge is going to be subjected to a lot of, vehicles passing by repeatedly. So that we can say it is a kind of cyclic loading. So finally, what does cyclic loading do to a particular element, to a particular structure? What it does is it tries to induce some fatigue, and there is some stress happening. So you say you are installing some sensor to read this cyclic loading. It could be in the form of accelerometers or strain gauges. So you install these sensors in the structure, and you develop a cyclic pattern of loading. So automatically your software, what it does is it tries to, as the load happens, there is a deflection happening. So the software itself develops it like a cyclic curve. So how do you
Right,
try to, deviate? So when the cyclic loading, when there is a, there's an unusual pattern in the cyclic loading, is when we can get to know that there's some unusual behavior of that particular element, and the cyclic loading has gone beyond a certain threshold. That is when we can tell them that there's something that is going on there. You need to go and check out, and see how the particular element is behaving.
So I would actually like to add what I said again, what's in the feature extraction. We have a certain set of data at the initial stage of a structure, and over years there can be changes due to in the dynamic behavior of the structure. So that when the comparison is done, we can always see an unusual patterns or any changes. That's when we can say, okay, there is actually something wrong, or there's some problem. So that's how we can actually detect that.
right. Do the periodical visual inspections in structural condition monitoring help in remaining aware of its condition apart from using sensors or any other surveillance equipment?
Yes, definitely. I think that is the main objective of SHM, that we are monitoring so that we can know that any problems or any it's just not for surveillance, but we should also see that that structure is right at its point and there's no problem with it, and it's functioning for its scope, and any unseen damages or any unseen failures have to be prevented. It's I think that surveillance thing is far beyond in the years, and now it's totally for the applicative measures what we are actually looking forward for.
So I mean, I just want to add to that. I mean, I think he was also asking, the person was asking about visual inspection. How do you compare visual and structural health monitoring? So
Yeah,
you have a, situation of structure which is inaccessible. So how do you go and visually inspect that structure? So in that time, structural health monitoring comes to rescue. You install some sensors which can tell you. You don't have to go there to that location and tell, and you don't have to see, okay, what is happening here. So visual inspective is, inspection is labor intensive. It is expensive. Imagine you need to send someone to the site every, say, 6 months for them to visually inspect how the structure is behaving. So that's why we try to always go in for the next step, that is structural health monitoring.
right. Next question is, can we depend on these transducers for 10-15 years to give undisturbed performance?
So I would like to take that question. As per my knowledge, what I know is transducer life cycle is around 7 years. As per my knowledge, so let's say that is still a better no point, because if I have to send a person every 6 months or every month, it is still better than sending a person for every 7 years and just replacing those transformers or any sensors. And even with it's just not transducers. I can also talk about sensors. When I say sensors also, it's always about the battery replacement. So that is still that still comes for over of years, rather than periodically going and attending. That is, I think, in that way it is always advantageous to use these.
Actually, even these SHM systems, when we have a lot of sensor manufacturers who come out with a network, like, they tell you, okay, you have this many sensors and this is the lifetime of that sensor. And sometimes they also offer you, offer you the conditions where they replace the batteries, like, it's like a warranty for us, if the batteries, say you're using a wireless sensor and the battery stops performing after, say, 2-3 years, and they have to obviously come and replace it for you. So like Sahana said, probably your sensors would last for about 7 years. And your budget, when you fix a budget for your structural health monitoring system, you always take into consideration all these factors. You will also be knowing for how many years you want to monitor this particular structure. It cannot be, indefinite. Obviously, you have a timeline. You say, I'm going to monitor this for the next 20 years. And then you have to
Right.
plan your sensor network accordingly. So that's how, obviously, sensors do have a lifespan of about, say, 7 to 8 years to our knowledge.
Right.
I am sure that as time progresses, even will people surely will come up with more better
Longer
lifespan,
lifespans.
longer lifespans, because since this is getting more and more attention and it's used everywhere, I'm pretty sure. I think it's not even 5 years down the lane, probably 1-2 years down the lane, there will be a better sensors which will run for a longer lifespan.
Yeah, actually, the
Right.
sensor qualities are improving day by day. I mean, it's not what we used to use, fiber optic sensors, and now we are in the age of wireless sensors and smart sensors, and the way in which things have is very dynamic.
Yeah. So on lighter note, be ready, ladies. We will call you in next 6 months or so for next advancement to hear.
Yeah, hopefully soon.
Right. Next question is, any contactless sensor then built-in sensors to pick up all structural information behind member surface needed for monitoring?
I mean, I think to my
And
knowledge, at
the
least.
second part of the question
Okay.
is, which will be better coverage and provide better accurate monitoring in real time?
So, I mean, what I could say is, see, for any structure, there are different parameters that need to be monitored. Like you have a building, for that matter. You have a column and you have a beam. So it's not only one So a strain gauge will measure the deflection. A temperature sensor will measure the temperature. So a concrete can crack due to temperature. It can crack due to deflection. So installing just one sensor cannot tell you, all how the structure behaves as a whole. You need to install this sensor in contact with that particular element you're trying to monitor, and you need to study what kind of behavior that particular element will exhibit in the next few years. So there's a lot of detailed study that goes into how you have to install the sensors, and the location of installation of sensors is very important. So you need engineering judgment, you need the expertise of your sensor manufacturers to finally install. So it is important that, it is necessary that your sensors need to be in contact with the particular structure you're monitoring so that you get your the relevant parameter that you need to analyze.
Right, accurate. Yes.
Yeah.
Could you name some heritage structures, including bridges, both in India and abroad, where these applications have been used?
So like I told you in my presentation, so this the Geoba Bridge in China, and I think even the Sydney Harbour Bridge in Australia has been installed abroad. What I can recollect, and in India, so there's a bridge in Tamil Nadu and Kolkata which I just saw, and I think even Vishalakshmi ma'am mentioned the Chenab Bridge, which has been installed with SHM systems. Heritage structures, there are quite a few in foreign countries. To my knowledge, in India, I'm not aware of any of heritage structures installed with these SHM systems. But in Italy, there are quite a few of the palaces, all the structures which have been installed with these systems.
I think India in... Yes, sir. Yes, sir.
Pardon, sir?
Signature bridge.
Yeah, signature bridge. Yeah.
Yeah, bridges, I think they are now they are starting to take care, and India surely is, I think now they're starting to realize the importance of it over a longer period of time. I'm sure in moving forward, we can see more of these systems in heritage structures as well, in all the heritage structures. I would like to say that.
Yeah. Could you explain about FBG sensors in SHM?
I think FBG is fiber Bragg graded
sensor.
sensors. It's one of the optical sensors. As per my knowledge, they are used to detect these physical parameters based on the stresses and the temperatures variations.
Right. In mode analysis, where one can get 20-year-old data to compare?
So, so there are different methods of damage identification. So 20-year-old meaning, say, like for an example, you are just when you're going to construct the bridge, you're going to install an SHM system. And a bridge is usually designed for us, a period of about minimum 20 years, I could say. So 20 years, so you're going to extract the modal parameters of that bridge when you construct, like I said, the first 2-3 years, we are going to obviously assume that the bridge is undamaged. So we can develop based on our displacement and based on the acceleration and vibrations of the bridge. We will obviously extract the data and develop certain mode shapes or frequency or time period of that particular structure. And 20 years hence, when you are going to extract this data again, obviously you can compare this with the old data. So data, like we said, data analytics and storage of this data is very critical, because we could always say, okay, 20 years old, how do we store this data? But it is possible now with the latest softwares and with the latest developments, it is possible to even access data that you have collected 20 years back.
To add on to that, like from the digitalization point of view, what we see, this machine learning and everything is all data feeding on which the predictions are made. So I think this is, as Ritika has suggested, this is one of the challenges we will face as well. So if we can compare similar structures with similar environmental background and operational facility, then we can surely use that data itself for this particular structure before we don't have to really wait for 20 years. We can already depend on the previous similar structures data, and we can say, okay, this can be the critical part and this has to be monitored, and we can always reduce the number of sensors or the reduce number of parameters which has to be measured. I think this is the future scope. I would say all engineers surely shouldn't restrict themselves to just structural engineering. Now the digital transformation has paved its way, and we should always be aware of it.
Correct. Manoj sir, we have maybe 7-8 more questions. Do time permit us?
Yeah, you can take, definitely.
Yes. Okay, there is one question from a UG student. He finds or she finds the topic really novel and interesting. He wanted to ask, how can I build on this domain?
Yeah, so I'll take that question because I'm also from an undergraduate background. So I did enter TC as a engineer trainee, and what I worked was on digitization. See, what I would like to say is be aware of what is happening. When I started, I was looking for all the softwares, because before it was all pen and paper, and now everything runs on STAD, ETABS, and everything. First, I would like to say know your domain clearly. The technical knowledge is very much important. If you don't know what exactly is happening in the technical domain, you will never know how to actually, even if you learn machine learning or if you learn data science topics, it's good you can parallelly learn it. But unless until you don't know what is happening technically, or how to structure behaves, or how the structural design is carried out, then only that's when you can actually find out, okay, I can use this tool, then I can apply this here. Okay, I can actually reduce this time consumption, or I can optimize this whole process by using this. What I call, like, predictive models are major of growing trend. So if you can actually use that knowledge here, but I think it's just not one part of it, not just the digitalization or not just the structural engineering part of it. It's always the 50-50, how you collaborate and use it. I would say, like, gain knowledge on both part of it. I think that's when you'll always come up how to utilize it in the future career. I'm sure, like, if you're moving towards that path, you will be in the more demand side of the market always.
I think now the demand is for digitalization. Everyone
Yes,
wants you to know, all Python and all the coding softwares and everything, so that you can apply it to structural engineering.
It's never restricted to computer science. I think it's in
Yeah.
future we can never say it's just
right,
restricted to computer
right.
science.
I think one of our audience wanted to ask that how do you ensure the huge data that is being collected through all these devices are properly used in taking necessary action, corrective action for the safety of these structures or the coming structures?
So,
So
yeah, you can take it, Sana.
Okay. See, there are certain softwares. I think one few software what Ritika mentioned in her case studies. But again, what we told is also a challenge is part of it. How do we, as and when there are a lot of data, I would like to stress on this, because we are, let's say, what one case study what she told has 333 sensors, so measuring around so many parameters. So when you're trying to derive a relationship between those data and the parameter, it can surely get complex, and that is where the a domain which is open for exploration, and we have to work on it. It still remains challenge, but still people are in abroad and all, they are working on it, but it can surely be optimized, and we can gain more better insights. Yeah, Ritika, you can actually add on to that. I think you have
Yeah,
told
I mean,
more
I
about
was just saying, yeah, I was just saying because Sahana explained in the presentation, like when you have so much data, like say you've collected this data from the sensor, you have to perform some methods like cleansing and normalization,
Right,
where you try to eliminate data which you feel is not going to be useful for your analysis. So see, these are the preliminary methods which has been adopted off late, but you have so much data that it's still a challenge. So we would always prefer where we can just feed the data to a software and the software can tell us. So we can't just sit and normalize data, cleanse data. So maybe we could, the next level, next future scope could be we just feed the data into a software and the software just is able to, tell you which is the unuseful data, which is the useful data, and how we can use this useful data for our
right,
betterment.
right. Another question is, we have discussed about the sensors which measure structural aspects of a structures like strain, deflections, cracks, etc. Do we have sensors to check the durability aspects of existing structure like chloride penetration, rate in concrete, or rate of rusting of the reinforcement, as durability is also part of SHM?
Yes, there are a few corrosion sensors as well. And when we say sensors, it always, when the reason why we say it is always attached to the material, it, as even in one of my slides, I did say it just doesn't say any physical deformations, but it also talks about the material, what we see, what we call as material science. It also says any irregularities in that material, like how Ritika said, when there's a crack, we'll know based on that material, concrete material material properties. So that's how we can also realize how about this chlorination effect or corrosion. There are specific sensors itself are installed for corrosion, I would like to say.
Right. What is the role AI can play in SHM?
Okay.
This is
Uh, so let's like I think I did talk about machine learning, artificial intelligence. If I have to talk about it, like Ritika told, now we are actually still figuring out methods where we have to separate the data, and this all has to be done in the presence of a data scientist or someone who has an
engineer.
experience.
Yeah.
Yeah, any engineer who has an experience. So maybe when AI enters, we don't have to sit in front of the system and say, this is the right data, this is not the right data. Based by observing pattern, it itself can come out saying, okay, this is the damaged data directly. We don't even have to normalize directly. It will come up with, say, probably this is the damaged data and this is where the location it might be having, and probably it will also can give us the remedial measures if we are feeding it with certain previous case studies. I'm sure someday in future we'll be able to reach that point as well.
I
Yeah,
think
it is still in
we we as
evolution
structural
stage. Yeah.
engineers, I think we feel that we need to be there to finally tell us, okay, this is damage and this is not damage. But I don't know. Maybe in the future, the software can tell us.
Sure.
We don't need human intervention for that.
Okay. Next question is, what will be the sensor range and active life of sensor? Can you detail? Can you give some details about the DAS system and what software is used for data analysis and evaluation of current condition of structure?
Okay, so sensors, see, there are different types of sensors. To answer the first question, the lifetime, like we said, to our knowledge, it says it comes to about 6 to 7 years. And you see the wireless sensors, for that matter, they are smart. You don't need to wire these sensors to the control unit or the remote control unit. So there is a certain distance up to which you can where you can install these. Have to be in close contact to the wireless sensor to the remote control unit. Say it could be about say 100 meters or so, and there is a limitation in using this wireless sensors because say you have a thick concrete wall and you have the sensor on one side of the wall and you have the control unit on the other side. And that time we don't go for a wireless sensor because there is difficulty in accessing that data, so and transmitting the data to the remote control unit. So that time what we do is we go for a wired sensor. So there is some, there is some restriction on the, up to which extent you can go, the signal, to where the signal can be captured, etc. And I think the next part of the question, could you just repeat the next part of the question, please?
Yeah, sure. Uh, can you detail about DAS system and what software used for data analysis?
Yeah, so like I said, there's a few softwares like LabVIEW which have been in practice, which have been used for this data analysis and data processing. This is one software that I am aware about, which can be used, and this data can be like it. I think for bridges, most commonly they generally go with this LabVIEW software, if I'm not wrong.
Okay. Right.
And to add on to that, wired and wireless sensors, both have their own advantages and disadvantages. What I and Ritika were actually
Agreed.
discussing about, when we say like wireless sensors are to be at a shorter distance compared to wired sensors, so the number of sensors required is also more, and they rely on Wi-Fi and other signals, whereas wired sensors don't rely on that. So there can be uncertainty in these Wi-Fi or signals as well. So both have their advantages and disadvantages, which will always be defined as what step I called as operational evaluation, where it will be defined, and that based on which only the sensors will be selected.
Yeah, and I think each structure need not have, only wireless sensors or only wired sensors. You can always go for a combination of both. When you feel like, okay, at this particular location, a wireless sensor is not feasible, that is when we try to, recommend a wireless sensor in that or a smart sensor. So it always comes with a package of many different elements, which can finally give you a very effective SHM system.
Right.
Amika, I have a small question to ask.
Yeah, please.
Yeah, either Ritika or Sahana can answer. Yeah, when you're talking about the wired sensors compared to the wireless sensors, how do you handle the lot of wires at the site and the data acquisition system? How do you take the data acquisition system over there to acquire the data from, if at all you are installing a around 300 sensors in a bridge. And
Yeah,
how
yeah.
do you take care of all these wires and the mess around them?
So yeah, wired sensors do. That is one of the main disadvantages of wired sensors, where
I agree.
it is very difficult to install these sensors because there are so many cables, and everything has to be finally connected to a control unit. So that is one of the major disadvantages of wired sensors. That's when wireless sensors came into picture. So that's when you it's like the next level, you development rather. You go from, so initially probably they used only wired sensors, and then they found some problems, and then finally they moved on to wireless sensors. So wireless sensors you can install, you don't need any wiring, and they have a battery of their own, and they can operate without being connected to the remote control unit, and that's how you can. But again, like I said, wired sensors also have, but wired sensors are much more inexpensive, I can say. Not compared to the wireless sensors are inexpensive compared to the wired sensors. So both together, they have some advantages and disadvantages. So together, we can see, depending on the situation, and depending if we feel like there are too many cables in that particular, column of that particular bridge, obviously we can go for a wireless sensor and try to get whatever data we need from that particular column, and try to reduce our, cabling.
But I think if you can plan the position of the sensors before construction, so you can also make the permanent provision for the cables also.
Yes.
Yes, sir. Especially if it is a very large structure. When we say SHM, it's not for always the small structures. It's always for a
Yeah.
huge structures. So it means that the monitoring has been already planned. So obviously, when we say instrumentation people, I think more than us, instrumentation people will be able to give a better light on this. As far I know, their work is that how the sensors are installed and how the wiring is done. So all that things are actually decided by them. And obviously now wireless sensors are coming into this thing, and now it's complete a package, I would say. Most of the wireless sensors, but yes, there are challenges from both the sides. We have to see how do we have to cope up with that.
Yeah. Heritage structure mostly made of stone masonry, as you told. Is there any particular software you suggest for masonry structural analysis?
So there is no analysis as okay. I think they want to know the data analytics software.
Yeah, yeah.
So yeah, see, you have a arch which is built of stone masonry, and you observe some crack in that. So when you observe some crack, you try to go and install a strain gauge or a displacement sensor on that, and then the reading that you get from it, obviously, like any other software, it's not that this particular software needs to be used. A heritage structure needs only this kind of software. Finally, the reading coming out of a sensor is the same. It's going to be a strain value or a stress value or a displacement value. And that data you can analyze using any software. So, there's no particular software as such for heritage structures.
And to add on more to that, more towards the advanced technology, what is a challenge again we have is defining those parameters, defining that relationship. Let's say if we have if they have the parameters that are defined, and the data and the relationship between those, I think any machine learning or any analytical software surely can be used to establish that analysis, or to bring out the decisions. But that's where the gap is currently, to establish that relationship, or how exactly is it dependent.
Yeah, right. How long do you suggest the period of monitoring and intervals of NDT should be done for a simple bridge structure? Any minimum period?
So, like I said, there are two types. There is a long-term monitoring plan and a short-term monitoring plan. So, if you feel like the bridge, a bridge it's a very important structure. When a lot of activities depend on that bridge, and the collapse or the deterioration of the bridge can actually bring down the economic activities of that particular country. And that time, the authorities are ready to spend so much on that bridge to install a permanent long-term monitoring system. So they can install it, right. So bridges will usually, they have a lifespan of about 25 to 30 years. So the monitoring could be done for that much period of time. And so it need not be that the interval set could be shorter. You don't have to monitor every year, say 30 years, you don't have to collect the data. You can set your interval as to what you want. Now, short-term monitoring, the example I gave was for the heritage structure. So when you feel, so heritage structures, you don't feel the need to monitor them unless you feel like there is some damage happening in that. When you observe some unusual behavior is when you try to go for a monitoring system. So then you go on, install a system for about 2-3 years, and then you try to analyze. So you don't need to install a system on a heritage structure for the next, for its life all over after that. So what you do is install a system for about 3-4 years, and then collect the data needed, and then perform the required analysis, and finally rehabilitate that particular structure so that its lifespan is improved and extended.
Okay.
I'll add to that. Normally, there are two types of monitoring. One is the condition monitoring, and the other is the health monitoring. Condition monitoring is the one which you do frequently for a particular time span, within a particular time span. The way we do for all the mechanical equipments, mechanical machinery, etc. And the structural health monitoring is the one which you want to monitor continuously for a given time period. It's not a frequent monitoring, but it's a continuous monitoring for the given time.
Given time, yeah. Right. So there is another question that can we, in the validation of structural design, how can we use sensors like life of structure, say 100 years, then what will be the life of sensors? How can we use sensors in the validation of structural designs? Can we have some relations or parameter or equations to relate?
So obviously, yeah, like structures will obviously have a longer lifespan of minimum of 15 to 20 years. We cannot say the sensors are going to have the same lifespan. Obviously, they will need replacement, and they will have to be, whether if it's a wireless sensor, you need to replace their batteries. If it's a wired sensor, you need to check the cabling or how it is, transmitting data to your control unit. So sensors do need replacement in between. We cannot say that they are going to be there throughout the life of that particular structure. So sensors are short-lived compared to your the structure that you are monitoring.
But again, adding to that, but whatever there's, as I told, the structures which we are monitoring are always bigger structures. Let's say an unforeseen circumstances where any failure happens, at that time the cost of building that structure is quite huge compared to this initial installation of the sensors. So in that aspect, I think structural health monitoring is always advantageous, because we always have unforeseen circumstances which we wouldn't have estimated. Even the code has a lot of provisions in design and everything, but we cannot clearly foresee future. So in that case, always a warning, what we call as precaution is better than cure, always comes into picture.
Right. In buildings and bridges, what parameters would you suggest for monitoring for long-term surveillance? And are there any codes internationally for SHM, for structural health monitoring?
So in bridges and buildings, you could say a common parameter would be a temperature sensor, which you have to install in both, and strain gauges, displacement sensor. So these are the common, any structural engineer would be able to tell you that these are the common, when we design a structure, we are going to apply all these loads, temperature loads and dead loads and live loads. And we are obviously going to check the structure for a column or a beam for deflection. So we know these are the most common parameters which we check even when we design the structure. These are the basic parameters which we also check even before the building is constructed. So we know while monitoring also, these are the parameters that need to be monitored. Your temperature of the particular structure. Supposing your bridge is located in very, dynamic temperature conditions in a very hot climatic region. So that time temperature plays an important role. And then you need to measure the deflection. Say you have a heritage structure, you have a column or a tall column or something like that. You need to measure the tilt of that particular element. So these are some of the most commonly used sensors for bridges and buildings. And also for bridges, we can say accelerometers are also very important because, there are a lot of moving loads on the bridges and bridges subjected to vibrational loads. So that time accelerometers play a very important role in
for old heritage structures, how to do data acquisition, including mechanical properties like Young's modulus, Poisson's ratio, and so on. Do we have any mechanism?
So like I said, when I gave an introduction on the bridge, I told you monitoring a bridge is a challenging task because we don't have sufficient information on how the bridge has been. We don't have drawings. We don't have information on the material of construction. So what we do is we try to observe the area of damage, and we try to see the moment we see a crack on that particular element, we try to measure and see that is that crack propagating. So there is no structural analysis done there. There is no, we don't try to find out what is the Young's modulus or anything. What we try to do is we try to make sure that the deflection of a particular arch is not beyond a certain threshold. And the moment it exceeds the threshold, we know, okay, there is something that needs to be done here and let's control this deflection. So that's the basic concept adopted for heritage structures because of this particular challenge that we don't have any historical data to compare that particular structure with.
That's where the re-strengthening of the structures comes into play. Whatever the based on the damage detected, they make sure to restore the strength with a lot of various techniques we have currently, and somehow extend the lifespan, and so that it's safe for any visitors to visit those heritage structures.
Manoj sir, we will go on with questions and questions and questions because our audience has given lots of questions.
I think you can wind up.
Anamika, may I say something?
Yes, sir, please.
First of all, I must thank both the speakers, Sahana and Ritika, for such an excellent presentation. And both of you have made me realize, you have made the ground shaky below my feet, because you made me realize that I am little out of date.
Thank you, sir.
And also I can tell you, the way we work, I realize that it has been changing radically, more so in recent years.
Yes.
And all these, digital tools and sensors which are now available, in fact, were unthinkable even a couple of years ago.
Right.
Yes, yes.
And the pace of change which is happening, it's like the kind of rate of change like in mobiles. We are seeing this in civil engineering. So far, I thought that the pace of growth in civil engineering was very, very slow. But I realized that, we are kind of competing with the another word, like mobile technology, which is changing every year. And what I realize is in this rapidly developing field, where digital technology is taking over, I think it is important for old fossils like me or even the middle level engineers to continuously upgrade themselves, to update themselves, and also if we do not upgrade ourselves and embrace the technology, we will not be able to utilize the younger generation, because they may have potential, but we may not, in the industry is not probably geared to utilize their potential. That is another challenge that we have. So, this is one thing which I wanted to share with you. And second, I would like to say that, these technologies are not a substitute to visual inspection. They are not substitute to non-destructive testing, because you see, there are also the negative side of these. They have to supplement and complement rather
Yes.
than, replace.
Correct.
Why I am saying this is because, you see, for example, when these computers came, and mostly what I find, the young engineers in our profession, they have little engineering judgment or the gut feeling, a feel for the structure, which is probably because of this automation. And therefore, I think it has to be a combination of visual inspection, non-destructive testing,
Yes.
and all these other instrumentation and the sensor digitalization, all these things put together will have to, because I mean this is future, no doubt. I mean, I think you started, Shahana, with this, that this is the future. Absolutely, I agree
Yes,
with you. Because you see, today, just let me give you some statistics. We have about 66 lakh kilometer of road, where we have about 1.25 crores of bridges. I'm only talking about the highway bridges. Add to it the railway bridges. And we, at present, we do not have the data of the condition of these bridges and assessment of their condition and timely retrofit these structures. I mean, leave aside the buildings. I mean, I'm only talking about the infrastructure. This is extremely important, and we can do it only through the digital technology. We do not have the labor, we do not have, the wherewithal to do it manually.
Yeah,
So
and it's
I
going to
think
be
this is the
expensive.
future.
Yes.
Yeah, this is the future, and we need to work whole hog. I mean, I think all the stakeholders have to drive this forward. And thank you very much for such an excellent presentation, both of you.
Thank you.
Yes,
you,
sir, Alok sir, I definitely agree. That's why I told that even for the younger generation who asked me, I'm a UG student. Like, yes, the advanced technology is there, but it's also important that you are technically well versed, because we should know exactly what results we are getting. Are they right? Are
Yeah,
they
yeah.
wrong? When we're using softwares, now we are using like analysis softwares, but are we sure that the analysis results what we are getting is right? So that surely depends on the technical expertise, so that can never be ignored. I think even in even moving forward, yes, this will be a complement to it, but technical expertise always stands first.
Over to you, Vishalakshi ma'am.
Thank you, Anamika.
Yes.
Thank you for moderating such a beautiful session.
My pleasure, ma'am.
Thank you, Ritika and Sahana, for enlightening our participants about the need of the hour, about structural health monitoring, which is absolutely the need for the future. Okay, as being a developing country, we all know how important it is to monitor the aging infrastructure, and with the advent of new smart materials. Okay, I think in the near future we might get some sensors which can be installed or embedded inside the concrete specimens,
Yes.
and where we can monitor the health of the concrete structure from its inceptions to the lifelong span of the concrete structures. Maybe we all look forward for that.
Yes.
Thank you,
Yeah.
Ritika and
Thank you.
Anamika. And
Thank you so much, sir.
Mr. Alok Baumis, who is instrumental for this webinar, in organizing this webinar. And thank you, Mr. President, for providing this platform for the women engineers to present their work and enlighten the participants.
Yeah, we will have
Thank
many such ram in the future.
Yes,
also.
yes,
Yeah, we will have.
definitely.
Thank you so much, sir. And I mean, we would like to thank Indian Association of Structural Engineers to give us this platform. I mean, frankly speaking, I think if not for this webinar, our knowledge on structural health monitoring would not have been to this level. And we got this opportunity to do some of our research and to explore more and, try to also put our focus into this. So we thank all of you wholeheartedly for this opportunity.
Okay, my last
like
question. I have one question.
Sir has one question.
Last question. Are you both member of ISTAC?
Not
No, sir. Not yet.
Then you should become the member of
you should
ISTAC.
definitely become a
And
member.
also ask your
Yes.
colleagues and friends to become the member.
Definitely.
Okay?
Sure.
Definitely,
Yes.
sir. We'll share about this. And again, I
Yes.
would like to thank everyone and Indian Association of Structural Engineers for this opportunity. I'm really a young engineer, and getting this opportunity at an early age, I think it's a very big platform for me. I hope I've justified that. Thank you.
I just want to say in my closing remark that we will send the link of this YouTube link to all of you. Kindly promote this recording and share it with all your colleagues and friends, so that they also get motivated and encouraged to come out and sort of give similar lectures. And we will provide the platform. ISTAC will provide the platform for young engineers.
Thank you.
And I would like more and more such programs to be volunteered by people like you. Thank you.
Surely, sir.
Thank you.
Definitely, we will do that.
Thank you.
Thank you. Thank you so
Thank you
much.
all.
Thank you. Thank you very much.